All right, should be recording.
Okay, so welcome people of the pre-seminar. We are a little bit late. We had a last minute change of room. I think now we are ready to start. Our speaker is Julius Benner, and he's going to tell us something about stone duality and its extension to Boolean inverse, semi-groups, and ample topological group points.
Yeah, thank you very much. Maybe I should start with an overview. So what is stone duality about? On the one hand, we have the category of Boolean algebras, and on the other hand, we have the category of stone spaces. So stone space is a totally disconnected compact Hausdorff space. I will get to it in a second. And stone duality says that there's an equivalent, or rather anti-equivalence of categories between these two. In one direction, if you have a stone space, you associate to it its closed subsets, so open and closed, and in the other direction, you associate it to a Boolean algebra set of ultimates. Just so that we are all on the same page, let me recall what a Boolean algebra is. Probably a dozen ways to say this. But in my talk, Boolean algebra will be a partially ordered set. Less than or equal that satisfies four properties. First one is for B and A, the infimum of A and B and the supremum of A and B exists. And secondly, we require that this wedge distributes over this V. So A wedge B wedge C is the same as A wedge B V A wedge C, and also the same with wedge degree swaps. Then thirdly, there are elements top and bottom such that for all A and A, bottom is less than or equal to A, less than or equal to top. And lastly, for every element in A, there's a negation of A. Think about that way. So there's an element not A which satisfies the following, A which not A is bottom, and A we not A is top. So we have some structure that behaves like from logical calculus. Maybe one example, take any set X, then the power set of X is a Boolean algebra. So the set of all subsets of X, and here the infimum of two subsets is in T, simply the intersection. And this not as of a subset with the complement. So X and so on. Okay. Explain to you what this side is. Now, what is a stone space? A stone space is totally disconnected. Compact also space. Well, you probably all know what a compact Hausdorff space is, but maybe let me recall what totally disconnected means. So this means every connected component is single. So totally disconnected means sorry, really what you would expect. Connected components are as small as they can get. And theorem, if X is a compact Hausdorff space, then X is totally disconnected. If and only it admits a basis of broken subsets. So that's it, both open and close. Yeah, I'm not going to prove this. But it will help us to prove the stone duality later. Okay, or maybe an example. So in general, stone spaces have a quite wide topology. Maybe the most famous example is Cantor or Cantor space, where you start with a unit interval and then you always remove the middle third in the first iteration, and then you are left with 2 unit intervals, and you in the next iteration you remove the middle section of those, and so on. And if you do this infinitely often, you end up with a set that I can't draw anymore, but still it contains points, and the topology of the space, or the topology which is induced by the Euclidean topology, is a totally disconnected concept. Okay. Yeah. Now that I've explained to you the basic objects, I can work towards the proof. And the essential ingredient of these proofs are filters, or more precisely ultimate filters. So let me recall what those are. for this part is postage. It's postage essentially or the infimum of A and B exists. And if I have given such a posit, I can tell you what the filter on this is. Is a subset of A in the filter and B in A. Okay. A is less than or equal to B, then also B is in the filter. So this property is called upwards closedness, and the second property for A and B in the filter, we also have that the infimum of A and B is in the filter. Okay, I call it's called no need. F is not a whole particle that set A, and it is called an ultrafilter. If F is maximal. So with respect to amount with proper filters. So how can you think about an ultrafilter? Let me give you an example. Take any set X and any element X. Then I can define an ultrafilter on the power set of X. I don't know this by Px, and this will be the collection of all subsets of X. It contain it contains X. So you can think about ultrafilters as generalized points, and I will get to that later. Yeah. I think that I think I get full that we will need. So now I can give you the proof. Here this anti-equivalence of categories between Boolean algebras and stones. Okay, but I've given you only the objects. So in these categories, what morphisms are what you would expect. So for Boolean algebras, these are maps that preserve the order, and for stone spaces, these are continuous maps.
And then it's automatic that the top thing is mapped to the top. And
Okay. So proof. So let me start by giving you the functor from Stone spaces to Boolean algebras. So Boolean algebras stop because it's a contrarian functor. And what it does is on objects sends a Stone space X to the set of open subsets. Is open. Now, the clone subsets form a Boolean subalgebra of the power set. And this is a Boolean algebra since X, the empty set, intersection of C and D, the union of C and D. What else? The complement of set C over C and D sets. Okay, so this becomes the Boolean subalgebra of the power set. Yeah, now, so we know this functor on objects, morphisms. If I have a continuous map into Stone spaces X and Y. And what else can you do is you want to get a map from the closed subsets of Y to the closed subsets of X here. You send C to the pre-image of C. The pre-image is preserved inclusion, so this is a morphism of Boolean algebras. So this is the functor from Stone spaces to Boolean algebras. Now, from Boolean algebras, so no, the functor from Boolean algebras, Stone spaces. This is a bit more complicated. For objects, I already told you what it does. It sends Boolean algebra to its set of ultra filters. So all U considering the ultra filters. And now this is supposed to be become a topological space. And how do we topologize it? To do this, we use that we have a map from A to the power set of the ultra filters. This map sends element 3 So the collection of all Doppler filters will contain A. This is a morphism of Boolean algebras. Why? If I have two elements of A and A is less than or equal to B, then any alpha filter with A also contains B. Yeah, but this was one of the axioms of a filter, upward slope, and so this means that say epsilon of A is a subset of epsilon of B. Now, what we can do with this fact, that this is a morphism of Boolean algebras, well, we then know that such sets is sorry. So I'm going to say what's okay, we have this is a morphism of Boolean algebras, and so if I consider the intersection of two of those sets, and this is the same as epsilon of the infima. So in particular, epsilon preserves infima, and also the complement of a set of the form epsilon of A is epsilon of this negation of A. And what we conclude is that the sets epsilon A of A give a basis for both sets based on sets for topology. The first equation here tells us that these sets do form a basis of the topology, and the second equation tells us that they are closed. More in effect, maybe we can write in this board.
Quick question. So
Yes.
to verify that the map was, so I need to check that it preserves the other and that it preserves the infima.
No, it's automatic.
Okay, I thought these two lines that we wrote here a intersection. Like that's automatic.
No, this is a conclusion of the fact that this is a morphism of Boolean algebras.
Okay, I thought that's something.
Where was I? Yeah. Okay. So this fact I'm not going to prove. So what you can show is that this is a compact Hausdorff space. Okay. And by what I've already told you, and the fact that totally disconnectedness is the same as having a basis of Clopen sets for compact Hausdorff spaces. I conclude that this is indeed some space. Okay, quickly running out of time. So maybe I conclude here the part of my talk about stone duality. What you would need to do at this point is to show that the functors they're not mutually inverse, but if you have, for example, a Boolean algebra A and then consider the Clopen subsets of the Ultra filters, and you have an isomorphism between those. So this is natural in A, and also for spaces.
About this line, so we checked that the preserve this map EA preserves for other, and then this implies these two lines. And the first one tells us that the EAs give the basis for the topology, and the second one tells us that it's
Exactly.
So,
Okay.
that's a question.
Okay.
On these here stone spaces.
Neues. So maybe you can do this and use this. So then I should give again do this.
Yes, but on the other side, Boolean algebras, it's not so easy to find a proper structure. So it will be interesting.
Yes.
You know, find the tensor product of Boolean algebras and extend this equivalence in a model level. Thing is, I don't know, but seems to be something new.
It seems natural thing to define a tensor products of groups. Yeah. Okay. Yes. Stone duality is very classical, and now what is this extension about? So we replace Boolean algebras by Boolean inverse semigroups. The paper I was following by Larsen, he did Boolean inverse monoids. So let me do this way. And what is a Boolean inverse monoid? Okay, so maybe there's not enough time, but very briefly, Boolean monoid is an inverse. Am I good? Yes. Also, the inverse semigroup means for all essence. We have a certain notion of inverse, which is defined by the quality property as inverse S, S, and F inverse S inverse. It's the same as F inverse. What this inverse semigroup which probably should have said. Okay, so that so it's a monoid, and there exists a zero element that is or S inverse. Zero times S is like time zero is equal to 0, and three properties should hold. The set of other tokens okay. Okay. Okay, don't have enough time, but maybe I should wrap up verbally. So for any inverse semi-group, you can define a partial order. We'll say T is less very good. S, if there exists an idempotent T such that S T is equal to S E. This defines a partial order on S is a non-trivial result, and then you can restrict the partial order in the set of idempotents, and you get Boolean inverse semigroups are precisely those for which this is a form in Boolean algebra, and then it should also add two other properties, which I'm not going to mention. And how you will then get a group point is you consider again the set of ultrafilters on this inverse semi-group, and you can define a certain multiplication, and this gives you a group point, and this is more properties that tells you what that it's an ample topological group point. Okay. Sorry, didn't have enough time, but I should wrap up now.
So in this equivalent, it's an equivalent of categories, right? So if you start with the Stone space and you take the token sets, you get the median algebra, and then you go back and take the filters. You get back the Stone space.
Then you get a nice so homeomorphic topological space. And the statement that this is an equivalence of categories means you have a natural homeomorphism. So it doesn't depend on which Stone space you start. You can always canonically define it.
Okay.
So the point was that the epsilon A that we go that forward, so this is not only a morphism of Boolean algebras, but even an isomorphism.
Yes, it's even a natural isomorph. So no exception that I define it as a natural explanation of the code sets an image, then it becomes a natural isomorphism.
So yeah, you can post that and you can just very basically what extra structure do you put on the category? Can you put extra structure on the category to show put an equivalence between Boolean and
Are you asking what structure the infima and so on correspond to? So I think the infima corresponds to the categorical product, and the suprema to the co-product.
Yeah, and then you express it.
And then this bottom is an initial element, top is the terminal. No, okay, I think it was the other way around.
That's how to express it. There are no more questions. Let's thank Julius.